Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we have Adam Lopez speaking to us. Adam is a PhD candidate at the University of Maryland. He's working with Philip Resnick there on statistical machine translation. And Adam's special interest is in making statistical machine translation algorithms scale up to extremely large data sets. And he's going to talk to us about an aspect of that work.
Okay, thanks. So this is, well, you can see what it is. It's a hierarchical phrase-based translation with suffix arrays. And I guess we'll just sort of get started. So I want to talk about phrase-based translation, and probably most people here have seen phrase-based translation before. We've got a phrase-based translation system, and the way it works is it's going to, we're going to segment our text into some sort of arbitrary length phrases, which are not necessarily linguistic phrases. And then we're going to independently translate each of these phrases. So the translation of each phrase is going to depend on this translation rule, which is shown here at the bottom, which is simply a pair of Chinese words and English words. Right? And so each of these phrases that we use in this translation involves a separate phrase pair. And so we're just going to sort of translate them in order. So the question is, so where do these phrase pairs come from? Well, we're going to extract them from a parallel corpus, right? So now if we imagine that this sentence is something that we saw in our training data, when we start out, we've got this sentence, our training data, we word align it. So we've got word alignments on this training data. And then those phrase pairs that you just saw are going to be, any pairs of these phrases that are consistent with this word alignment, right? So these are the phrase pairs that were used in that translation. However, in the course of rule extraction, we're going to find not just these phrase pairs. We're going to find a whole bunch of other phrase pairs that are also consistent with this word alignment. So when you're extracting rule pairs for a translation system, you're going to get dozens or possibly hundreds of phrases per sentence. And so what this looks like in a standard phrase-based architecture is, I start out with a parallel text. I'm going to, extract all of those rules, and again, I might have dozens or hundreds per sentence. And then I'm going to score those rules. And then when I actually want to translate, I've got this big flat file. I'm going to load that up into memory, and then I'm going to decode with it. So one of the problems here is that so we start out with this parallel text. We might have millions of sentences in our parallel text. And we're extracting dozens of phrases for each of those sentences. And this gets big in a hurry. So we've got a very big text. We've got a very big rule set. So actually just extracting and scoring these things is going to take several hours. And the other thing is that the rule set doesn't depend just on the size of this text and the number of phrases that come out, but actually the length of the phrases that we use. So, if we restrict ourselves to a length 3 phrase, then it's going to be one size. If we add, if we want to go up to 4 phrases, we add. Essentially, it grows linearly in the length of the phrases that we allow. So one of the things that we're going to have to do in order to sort of make this tractable is we're going to have to restrict ourselves to very short phrases. And so this is something that's typically done. And there's some debate over whether we need really, really long phrases or not. I found in some experiments that we get benefit going up to even like 8 or 10 phrases of that length. So, but normally in a system like Pharo, that's sort of the standard baseline. We have phrases of length 3. So that's one sort of trade-off we have to make, is we have to sort of restrict the size of these phrases. And the other thing that we typically do to sort of make this tractable is, at least in research systems, is I've got these millions of phrase pairs in there, and now I want to decode maybe 1,000 sentences for something, one of the NIST test sets. I don't necessarily need all of the rules that I've extracted from my million plus words of parallel text in order to translate 1,000 sentences of NIST data. So what most people do is we filter this set down, so it takes less time to load into memory. It loads faster. But at this point, we've turned our nice machine translation system into a batch processing system, and the only thing it can translate is that data. So for instance, if you ever tried, say, translating, the NIST MT06 set with rules that you filtered on the NIST MT05 set, the results are terrible because the rules that you get out when you do this filtering are very specific to the test set. But the problem is because we're doing offline phrase extraction, we're going to have to extract everything at once, and then we do the filtering later. So there's an alternative way to doing this, and that is rather than to do this phrase extraction offline, we do it online. And so the way that we do this, this was actually proposed independently by a group at Edinburgh and a group at CMU a couple years ago. And the basic idea is as follows. Rather than do all the extraction offline, I'm going to actually load the parallel text itself into memory. And then what I'm going to do is when I receive an input sentence in the decoder, I'm going to make a list of all the source phrases that I might possibly want to translate in that text. And then I'm going to do some online pattern matching in the source side of the parallel text to find those things. I'm going to extract their matching translations, and then I'm going to score those rules, and I'm going to send those sentence-specific rules back to the decoder, and it uses them to do translation. There's some additional problems here with figuring out how to do the extraction and scoring very quickly. Those were worked out in these previous papers. So this is basically what we're looking at here, and what this talk is going to be about is online pattern matching, right? So the online pattern matching problem. So in a normal pattern matching problem, I have some large text in which I want to search for a pattern, and I'm given the pattern, and I just go look for it. So the difference here in phrase-based translation is that I'm given this input pattern, and now I'm not looking for this input pattern. I'm looking for all of these input patterns, which are all essentially of the contiguous substrings of the input pattern that I'm given. So I want to look for all of these possible contiguous substrings, and then I'm going to extract rules for each of those contiguous substrings, and then I'm going to use them to translate. And so the way that this online pattern matching works, it's based on a data structure called a suffix array. So if you haven't seen suffix arrays before, they're quite simple. The basic idea of a suffix array is I have some text. And so in these examples, my text is going to be an English text, right? But remember, what we're actually doing, we get Chinese in and we have a suffix array on the Chinese text. But I'm going to assume that maybe not everyone here reads Chinese, so these examples are in English. So here's my suffix array. Well, here's my text. So this is an English example text. A suffix of a text is simply going to be any string starting somewhere in the middle of the text and going all the way to the end of the text. And the nice thing about this is each suffix can be uniquely identified by the index of its first word. So for instance, suffix 4 is the one starting at position 4 and going all the way to the end of the sentence. Now if I take all of these suffixes, right, they don't quite all fit on the screen. I take all of them, and then I sort them lexicographically, right? So now I've sorted all of the suffixes. Now if I look at the associated suffix ID, this thing right here is the suffix array, right? So here's the suffix array for this text. The suffix array is actually just a permutation on the list of all of the positions in the corpus, right? So now what I want to do is, say I get an input pattern in that I want to search for. How do I do this? So here's a pattern that I want to search for. And now, because this suffix array represents the suffixes of the text sorted in lexicographical order, I can do binary search. So I start out in the middle, and so the middle, the suffix that appears in the middle of the suffix array corresponds to that word. So I essentially do a double dereference to look up the actual words, and then I just compare them with my query pattern. It turns out lexicographically, this is larger than the query pattern. So, I divide in half and I just do the standard binary search. I look here, this is still bigger, so now I cut in half again. And now I found my query pattern. And possibly, the query pattern may occur multiple times. In the case where it occurs multiple times, I'm actually going to find a contiguous run within the suffix array of all the positions where that substring occurs in the text. Right? And so the complexity of doing this, sort of a naive way of doing it, is going to depend on the length of the query pattern times a log term on the size of the text that I'm searching in. Right? So the original suffix array papers show that if you have an additional data structure called an LCP array, we can actually do slightly better than that. We don't have to multiply those two terms. We just take the sum of them. So this is a bit faster. And actually, it's recently been shown that with some additional data structures, you can actually do this query in optimal time. But for our purposes, actually just doing even the most naive algorithm up there is going to be plenty fast. In fact, I'm not sure about the implementations that we just saw. I'm sure they don't do anything better than the Manburn-Myers algorithm, which is logarithmic in the size of the text. So that's how we do this in phrase-based translation. But yes?
That's if you have random access memory.
Yes. But for this talk, we're going to assume random access memory. So
more relevantly, that memory that is large enough to fit your entire
so this is actually a good point. I should have mentioned earlier, but actually, if you take, at least in the examples that we've seen in the work that I've done, and also in the previous work, actually storing a numberized corpus in memory, the entire corpus, actually takes up much less memory than storing the phrase table that I would otherwise extract. Because the phrase table actually has a lot of redundant information in it. And so sort of paradoxically, actually just storing the data itself in memory is a much more compact representation. And the nice thing about doing this, and the reason that they did this actually, is that now, because I can look up the patterns online, I don't have to restrict myself to any particular phrase length. We can use an arbitrary phrase length. And so you can imagine you can't even store a sort of an arbitrary phrase length.
Is it okay if I ask a question? I should keep to that. So it's of course true that if you store the entire corpus, it's much smaller than storing the entire phrase table,
yes.
Right? But in a suffix array representation, you actually access that entire corpus, more or less. I mean, basically, I'm not familiar with what the locality of reference is in the suffix array, whereas in a large phrase table, your locality of reference is such that you don't actually touch large chunks of the phrase table.
So it depends on sort of how you implement the phrase table. So you might implement it in, say, like a prefix tree data structure. In that case, you actually are going to be sort of moving through different points in memory. In this case, so yes, if you're worried like about cache misses, then you might have some problems, because doing the search in the suffix array, we're going to touch large portions of the suffix array, and then once we find the patterns, they could be anywhere in the text, and so we're going to have to access all those patterns. So the locality is not necessarily great. In general, I'm going to assume that we have everything in memory. So does that sort of answer your question?
Yeah. I mean,
all right. So this is the sort of the architecture for phrase-based systems. And now at the University of Maryland, we have a hierarchical phrase-based system. So this is a slightly more involved than a standard phrase-based system. So in a hierarchical phrase-based system, we can still translate contiguous phrases, but we can also translate what we call hierarchical phrases, where hierarchical phrases can have gaps. So it's a sequence of words and also elastic gaps. And so what that means is that this rule, this rule, when I apply it, can apply to a gap of length 1 or maybe a gap of length 3. It can stretch. And the extraction algorithm is sort of very similar to the phrase-based extraction algorithm. But the problem with these gaps, this is maybe not a great example, but you can also have word, gap, word, or 2 words and then a gap and followed by 2 more words. So these are basically phrases with discontiguities in them, right? And this is not exclusive to David's system. There are a bunch of other systems that use source phrases with gaps, some of which you've probably heard of. So the set of discontiguous phrases now for an input sentence is going to include all of the contiguous phrases that we saw before. And in most of these systems, they're basically going to be a superset of the contiguous phrase-based rules. But they're also going to include all of these phrases with gaps in them, right? So we don't just get the contiguous phrases, we get all these discontiguous phrases as well. And we're even going to get a few more. Yes?
Can the variables be at the beginning?
Yes, actually, so in addition to these patterns, you can actually have variables at the beginning and the end. For our purposes, I'm not going to talk too much about that. It's going to require some adjustments to the algorithms I'll show you later. But for our purposes, we don't worry about it too much. And the reason is because if I have a gap at the beginning or end of one of these, it's the lexical portion of the rule is identical to one of these things, right? So in terms of searching for it, I'm actually looking for the lexical items that match. It's going to be identical. And so now the question is, can we adapt this online pattern matching search to this problem where I have phrases with gaps in them? So obviously, one reason we might want to do this is, as in the case before, we don't have to filter, we don't have to spend a lot of time extracting rules, and also we can potentially use arbitrary length phrases in terms of the number of words it contain. And then the next question is, what else can I do? If I can look up the phrases online in the parallel text as I'm translating, what else can I do with that? And I have an answer that I think is interesting, which I'll tell you at the end of the talk. But you might want to think about what kind of things you might be able to do with this. So here's the problem statement for this work. So given an input sentence, I want to efficiently find all of the hierarchical phrase-based translation rules for that sentence. And what do I mean by efficient? This is actually going to depend on our context, but let me tell you about the decoder that we're using. This is a Hierarchical. It's David Chang's decoder. This is actually the version from his computational linguistics paper that is either in press or has just been published. It's written in Python, and the decoding time is about 10 seconds per sentence. So you can compare that with whatever decoding time your own decoders use. And so for instance, a C implementation might be 10 times faster. But in terms of efficiency, when I mean I want to do efficient lookup, what I mean is I don't want to slow down my decoder by an excessive amount of time. So if it takes 100 seconds to look up rules, is that efficient? I mean, the question is, how much time hit can I take to actually look up the rules? So now we're going to look at pattern matching with gaps. Right. So let's suppose I have this query pattern. The obvious or the solution we used in the contiguous case of doing binary search is not going to work. Right. So if I look at this, which of the suffixes in this corpus are prefixed by this pattern? Well, it's these. And you'll notice we have a problem. It's not a contiguous section of the suffix array. Right? So I've got him and it, and I've got him on and it, and I've got him, period, it. So those things all match that pattern because the stuff between him and it, they are just elided by this gap. And it's actually worse than this because you might notice in a couple of these cases, the pattern actually occurs multiple times on the same suffix. So doing binary search, both of these are problems for doing binary search. Binary search is not going to work here. And so now the question is, if you're going to solve this problem, if you want to look up these patterns with gaps, how are you going to do this? And if you thought about this and implemented it, you might come up with something like the following. What I'm going to do is I'm going to decompose this pattern into a set of contiguous subpatterns, right? So these are the parts that don't include the gaps. Now what I can do is I can look up the first contiguous pattern using a standard suffix array lookup using binary search, and then I'm going to look up the other contiguous pattern, right? So now I've found the subpatterns, And what I need to do, so now I have the list of locations where all these things occur, and now basically what I need to do is compare this list of locations with each other. So essentially what I do is I want to know when one pattern occurs within some elastic window of the other one, and I'll come up with a list that looks something like this. Right, so this is simply based on comparing all of the elements of these two lists to each other, right? And if you had implemented this algorithm 2 years ago, you would have the state-of-the-art algorithm for pattern matching, right? This is the state-of-the-art for pattern matching with these discontinuities in your search queries. So now you notice I've elided over some of the details. Actually, comparing these lists of locations with each other in order to extract out the places where things actually occur within some distance of each other requires a little bit of computation, obviously. And so in the Raman algorithm, what they do is they take the list of locations. First problem you may notice, these things aren't sorted. Right? They're sorted by lexical graphical order, but they're not sorted in terms of locations. Right? So in order to compare things, you can imagine if they were sorted, well, that would make things much easier. I could sort of go down a list line by line and do something that looks kind of like a merge algorithm. But since they're not sorted, this introduces an additional problem. We don't want to have to compare every element with every other element. That would be n squared. You might sort them, probably use some kind of n log n sort. And the Raman algorithm uses something rather clever to sort these. It's called a stratified tree. And this is... you may know this data structure after the name of its inventor. Sometimes it's known as a Van Emdy-Boas tree or Van Emdy-Boas priority queue. It's a very clever recursive data structure. I won't describe exactly how it works, but its salient characteristic is that all of the operations take log t time. So the full algorithm for this pattern is I'm going to sum over all of the subpatterns. Log t times I'm missing an ni term. Sorry, I'm missing a term there, but it's log t also times the number of occurrences of each of these things, which will denote ni. And so it turns out that actually you can do slightly better than this if you assume for each pattern it has if we create a hash table where the hash ID is basically the sentence ID of the pattern. And so then I have a hash table that's the size of the number of sentences. I simply throw each location into the associated sentence. And so then I get something that's much closer to linear in the number of sizes, the number of occurrences in the pattern. Right? So we implement this algorithm and we run it on some data. So we've got 20 million words of Chinese English following these characteristics. I'm only going to use 50 test sentences. So we're basically going to look at runtimes here. And I'm going to implement exactly David Cheng's model, which has a number of constraints on the number of words and the size of the gaps and the number of gaps that you can have. And so if you implement this algorithm and you run it, it takes a while. It takes over 2,000 seconds. By the way, that's 2,000 seconds per sentence, right? So it's over 30 minutes per sentence. Now, granted, we could re-implement it in C, and it would get somewhat faster. But then, of course, you would re-implement your decoder in C, and now you're still going to have an order of magnitude, 2 orders of magnitude increase in the decoding time if you implement this algorithm. So, yes.
Go back to the previous slide. So what does minimum training gap size 2 mean? Why is there a minimum on the gap size?
So what that means is when I'm extracting a pattern, so if in my training corpus I have 4 words, I can extract the pattern AXD because it spans 2 words, but I can't extract the pattern AXC because that only spans 1 word.
What's the rationale?
The reason, so this was actually in David's original implementation, and the reason that he did this is essentially to avoid a ridiculous amount of spurious ambiguity, because you could essentially replace every single word and every single rule with a gap. it's I don't actually have the numbers on that, but apparently it blows up the grammar by quite a bit. But the difference, so the reason these are distinguished is because when I'm decoding, it's okay to have a gap size of length 1, but it's just in the training size that we implement this. And so the algorithm I'm going to show you, although the timing data depends on these limits, the algorithms themselves don't depend on them in any way whatsoever.
Your max words is the number of actual lexical items, not counting the gaps.
Yes.
And max length 10 is?
The total length that the pattern can span in the training set. Right? And so it's slow. So why is it slow? So it's useful here to compare with the contiguous case, right? In the contiguous case, I have all these patterns, which I denote W, and there's the lookup time that we saw earlier. And now in the discontiguous case, now I'm going to have to sum over the patterns, and I'm also going to have to sum over the subpatterns of those patterns. And so the sum terms are basically equivalent here, and the pattern length term is basically equivalent. The log term is equivalent, but now I have this extra term, which is the number of occurrences of the pattern in the corpus, right? So to make this concrete, in our data, there are roughly 137 rules per source sentence, and you can see there's the pattern length and the log t. So log. Actually, I think the log term, I think it's actually 25. But in any case, it's not hard to see that this can be done, on your millions of instructions per sentence processor, right? This is going to be very fast. But now let's look at the discontiguous case. Now we get some extra terms in here, right? So there are two problems actually. One is that the number of rules that I have to look up is much, much bigger, right? There are many, many more hierarchical rules that I can find. And the other problem is this term that's based on the number of occurrences is absolutely killing us. Now that's averaged, and obviously we have a ZIF distribution, so there are plenty of patterns that only occur a few times, but then there are some patterns that occur over 1 million times. And so this is really, really bad. So the algorithm that I'm going to show you that solves this problem, to some extent, is going to address both of these problems. So they're different parts. So first we're going to solve the number of lookups that we have to do, and then we're going to address the number of occurrences, that term there. So the first thing that we're going to look at is cutting down on the number of lookups that we have to do. And so this is sort of an extension of one of the contiguous phrase-based algorithms. Actually, it's quite a bit extended. And this is from the Zhang and Vogel paper. And here's the basic idea. Let's say we want to look for this query pattern. Well, it turns out that we want to look at the maximal prefix of this pattern. So if I want to look for a source phrase him and, I'm also at some point going to want to look for its prefix pattern, right? So perhaps what I should do, the first thing I should do is look up the prefix pattern and find the locations where it occurs in the suffix array. Then, because this is a prefix and because my suffix array is in lexicographical order, I know that the longer pattern is going to occur somewhere within the range that the prefix pattern is restricted to. So rather than do a binary search on my whole suffix array, I can just do a binary search within that section. Now we already saw that actually doing the binary search for contiguous patterns is really fast, and so they get a little bit of a speed up from doing this. But we're going to apply the same principle to discontiguous phrase lookup, and the benefits are probably going to be much, much bigger. So let's suppose that we have a query pattern that has a discontiguity in it. So we have a gap in this pattern. So the maximal prefix for this is, including the gap, all of those words there. And so suppose we've computed its locations. Remember, the list of locations is actually a pair, which is basically, in this pair, the starting pattern of each of the contiguous subphrases, right? So what we'd rather do, or what we'd like to do, is we'd like to start looking for the longer pattern within the set of locations that's defined by its prefix pattern that I already found. But we can actually do better than this, because in addition to this, in addition to having a maximal prefix, we also might want to look at the maximal suffix. Right? So the maximal suffix also defines a set of locations, and clearly the query pattern is only going to occur in some location that's offset by 1 from this maximal suffix. Right? So now what I can do is I can actually just compare these lists of locations and see if that offset condition holds, and then I get my answer out. Right? So basically what we're doing is we're sort of exploiting redundancy. Because, again, we're looking up over 7,000 rules, but our sentence length is about 29. So clearly there's a lot of overlap going on there. So what we're trying to do is exploit all that overlap. But there's some other overlaps we can exploit. So, for instance, so say we want to look up this sentence and we want to find all the patterns of the sentence. All of these phrases and discontiguous phrases that we might want to look up actually occur more than once in the sentence. So rather than look them up each time for each occurrence in the source sentence, I actually am going to look them up just once. So now what we're going to need some kind of data structure to sort of manage this process. And the data structure we're going to use is a prefix tree. So a prefix tree is just deterministic, non-minimized deterministic finite state automata on the set of patterns. So this prefix tree is going to potentially incorporate all of the possible hierarchical patterns that we might want to look up. And so we're going to, in addition to using the prefix tree, which makes it very easy to figure out which pattern is a prefix and another pattern, we also want to look at suffixes, recall. So we're going to augment this thing with suffix links. So in this case, a suffix, so each node here represents a unique pattern. Right? So this pattern, this node represents the pattern it, x, him. So the suffix link from this node is going to point to the node representing the maximal suffix of this pattern, which is x, him. Right? So that's how the suffix links are determined. And so now, since our lookup is going to depend on maximal prefix and maximal suffix, you can imagine it's sort of a recursive algorithm. So I'm going to describe it somewhat recursively. And we have to have a recursive base case. So in this case, we're going to initialize our algorithm. So when I'm going to build this suffix, this prefix tree with these suffix links, I'm going to have 4 types of nodes during the construction. There's a root, which is always fixed. Then I'm going to have unprocessed nodes. I'm going to have active nodes, which represent patterns that I found, that I have actually found instances of in the corpus, which means that I might want to look for extensions of those patterns. And I'm also going to have inactive nodes, which represents patterns that I looked up and didn't find. In that case, I know I don't need to extend anything past an inactive node because I'm obviously not going to find it. Yes?
So maybe everybody else is following this, but just to make sure, right, that I'm not so sure I'm following. This prefix tree is being built from the parallel corpus from the side of or it's being built from the training data? So the prefix tree, this prefix tree is going to be used to manage the pattern search for a single input sentence. So it's being built from a single input sentence.
Yeah, so when I got my input sentence, I'm going to use this prefix tree to generate the list of patterns that I found, and also to make note of patterns which I didn't find, so that I don't have to search for any patterns that are prefixed by those.
In other words, instead of searching for each pattern separately, this is going to give you a way of caching.
Yes, exactly. That's exactly right. And so essentially what we're going to do, we're going to build the prefix tree out by depth. So we're going to have a frontier, and we're going to process in iterations that are based on depth, which is defined by the number of lexical items in the pattern. So first we're going to process all of the rules that have 1 lexical item, then all the rules with 2 lexical items, and then so on. Right? So the way this works is I start with my root node, and I'm going to add an edge from the root node for every single word in the sentence. And then I'm going to add onto agenda a node label and also a position in the sentence which represents essentially the next position that I'll need to process in processing this pattern. So And so if I add this node into the tree, the question is, what's its suffix? Where should its suffix link point to? So if I have a length 1 pattern, the suffix link should point to the root node, because the root essentially represents a 0 link pattern. And so now I can do this, for some of the other words. And then when I get to this word it, which already appears, well, it turns out there's already an edge labeled with it from the root. So now I don't need to add another node for that, but I am going to add an item to the agenda that says, I'm going to look at that node again, and so possibly I might have to extend that pattern that node 1 with both persuades and disheartens. Does that follow? So later on, now I haven't actually looked up any of these things yet. I'm just putting them on an agenda of items that I'm going to look up later. And so I continue to do this for the rest of the words in the sentence. In addition to this, I also remember we might want to have patterns that start with a gap. So I'm also going to add a node for that. And because there's no lexical item associated with this, this is just automatically marked as active, which means I already found it trivially because there's no lexical item associated with it. In addition to this, I'm also going to add all of the words again in the sentence starting from this X node. So I can essentially have all the patterns that I want to look for prefixed by that gap. And so now where does the suffix link come from here? Well, to find the suffix link of any node in the tree, I look at the parent node, and I look at the suffix link of the parent node, and I find the edge with the label of interest. So in this case, I look at the suffix link of this X node, find the persuades edge, and then I add the suffix link to that edge, to that node. Right? And so now I can do this with all of the rest of the patterns again. And so this is essentially the way I initialize this prefix tree. So now I'm going to have to do with processing all these nodes. And so this is the recursive case. And there are 5 cases, but they're actually really simple, so we can go through them really quickly. So let's say now this is just a partial prefix tree, but let's say I'm in the middle of processing my prefix tree, and the next item on my agenda is node I, which points to this white node over here. So case 1. In the first case, node I is unprocessed, which means I have to do something to it. And recall that I want to look at its maximal prefix and maximal suffix. Well, I already know what the maximal prefix is. It's the node that's its parent, and I have a suffix link, so I can look at those 2 nodes. I'm going to have cached the location information of those 2 prefix and suffix patterns at those nodes. And so I'm going to use that cached information to compute the location of this thing. And assuming that I find it, then I'm going to extend it with both, oh, that's not labeled. This should be X, him, and disheartens up here. So I'm essentially going to extend that with information from I at from it at position 4. So I can extend, and I add the 2 new nodes to the agenda, and I also add the appropriate suffix links, which I'm not showing here. So now the second case is I get to the node and it's already been processed. And the reason this might happen, you saw earlier, I added the node, the first node labeled with it onto the agenda twice. And so when I get to it the first time, I'm going to process it and I'm going to add any extensions to it. But in this case, I get to it, but from a different position. And so I want to add extensions from that position, so I just add them. So the node is already active. I don't have to do any lookup for it. But I do have to add any other patterns that it prefixes. So case 3. So in case 3, I get to the node, and again, in this case, it's unprocessed. And so again, I look at the maximal prefix, maximal suffix, and I compute the location. And it turns out this pattern doesn't occur in the corpus. So in this case, I mark this thing as inactive, and I say, I'm not going to do any pattern search past this point. I don't have to add anything on the agenda. It just stops here. Right? So and this sets up case 4, which is sort of obvious. So in case 4, I have a node that's unprocessed, and it turns out that its maximal suffix does not occur. So I don't have to do any work here. I can just mark it as inactive. Right? And the final case is actually analogous to one of the cases we saw earlier, which is I get to the item on my agenda, and it turns out it's already been marked inactive. I don't have to do anything. I just keep going. Pull the next item off the agenda. All right. So we implement this prefix tree, this sort of way of exploiting all the redundancy in the list of patterns that we're looking up. And we implement it, and here are the results in terms of the number of computations that are performed. So by the number of computations, I just mean the number of actual sort of collocations of contiguous patterns that I have to compute. And we cut it down by a lot. Right? So the number of computations that I actually have to perform goes down by quite a lot by using the strategy. There are a lot of things that I don't even have to look up at all because I find out in advance I don't have to look them up. And so now let's look at the timing results.
Are these numbers
yes.
percent?
No, actually these are raw numbers. Percentance divide by 50. I'm not going to do it in my head.
Okay.
But yeah.
The total for the
yes, this is total. Yeah, this is total for the whole set. I'm sorry that wasn't very clear. But the timing results actually are percentance. So here's the timing results, and here's the baseline that we saw earlier. And so now we implement the prefix tree, and well, we get a reduction, but it's maybe not so great. And so the reason for the disconnect between the number of computations I perform and the actual time that I save is because a lot of the computations that we're saving time on are things that are rare, or things that don't occur at all. So a lot of times I'm doing work to try to compute things, to look up things that actually don't occur, and maybe it's not actually that much work because it involves subpatterns that are fairly long and are infrequent in the first place. So I do get some time saving here, but it's not as much as I would like. But in any case, this is how we manage that process. I do want to say one other thing about this. So this prefix tree data structure that I built over the input sentence and its patterns, I don't want to do batch processing, so I'm going to have to erase that after each sentence, because otherwise I'll eventually run out of memory. But if I do want to do batch processing, I can actually just keep that thing in memory. And so I can actually exploit redundancy in patterns between sentences. Right? And so there are any number of sort of partial caching strategies you can imagine in between those two extremes. So now let's look at some complexity analysis again. So now we've dealt with the first problem. Now we want to deal with the second problem. So now we have to deal with the fact that the complexity depends on the number of occurrences in the corpus of these patterns. So let's do some empirical analysis. If I take all of the computations that I have to do, and I sort them by the amount of time it takes to do them, and then I plot those on the x-axis, and then I compute the cumulative time, it looks something like this. Actually, it looks exactly like that. And so what is this telling us? It's telling us that essentially all of the time that it's spent is spent processing a very small number of patterns. And this shouldn't really be that surprising. It's because the distribution of patterns in the corpus is a zip distribution. And so recall that that term that depends on the number of patterns is really only a problem in this danger zone over here. So this is the area, these are the pattern types that are causing us to do all of this computation. And the rest of these pattern types actually aren't causing us a ridiculous amount of work, they're causing us some amount of work. And so now there are basically two cases. I could have a frequent pattern, something in that red area there, that's paired with an infrequent pattern. In that case, the complexity is going to depend mainly on the size of the thing that occurs all the time. Or the other case is I could have two frequent patterns. Right? So I'm going to show you two algorithms to deal with both of these different cases. Yes?
So this is the number for your 50-sentence corpus, right?
This is actually the distribution of patterns in the training data.
Oh, in the training?
Because it's their number of occurrences in the training data that's costly.
Because I'm just taking a look on the right-hand side. That's 60,000, right? I was just wondering, can you just remember all the patterns that occur more than 100 times?
That's pretty close to the answer, actually. But I'll show you that in a minute. But basically, we have two cases. We got frequent. So maybe I have a pattern that occurs, 1 million times, and it's paired with a pattern that occurs 10 times.
When you say paired, you mean source and target?
No, I mean that. So this is A, this is B, and I'm looking for A, X, B. Right? So, and the other case is, I've got 1 million, and then I got 900,000. Right? Both of these contain something that's frequent, but we're actually going to deal with these in somewhat different ways. So first I'm going to show you how we deal with this first case, which is I got a frequent pattern pair with an infrequent pattern. Yes. Oh, sure.
So the pattern is A or B and or A and B. What are the pattern scale?
Oh, these are actually the number of contiguous patterns.
Contiguous patterns.
Right.
So A or B.
Can you just say what that x-axis is? I mean, it looks to me as if there's only like
the x-axis is
40,000 patterns that have count greater than 1, if I'm reading that graph correctly.
That's probably true, actually.
Probably right.
Yeah. There are a lot of infrequent patterns.
But this is the number of patterns in the training data, right? I mean,
yes, by type.
Training data.
You're saying
by type.
You're saying take a test set, find all the patterns in that test set, and then count how often they occur in the training corpus?
All right, so what I'm saying is, I take my training set. I take my training set.
So it is relative to the training
Yes,
set.
this is relative, because these numbers depend on how many times it occurs in the training set.
So with the fact that you've only got 60,000 unique patterns in your training set,
these are actually
training set?
Yeah, so these are so there's an error here. This is actually unigram patterns, and the 0 term is because this is on a log scale.
Yes,
I apologize for that.
So that's actually really fun, right? Yeah.
So these are unigram patterns. Actually, bigram patterns and trigram patterns also follow the same distribution, but they're obviously they have much longer tail and they don't go up quite as high. But those are also a problem as well. So I apologize for the confusion. Graphs maybe not so clear. Okay, but does it follow?
Yeah.
So now we're going to deal with this case where I've got a frequent pattern paired with an infrequent pattern. So I've got a frequent pattern paired with an infrequent pattern. And so the way this comes about is, remember, first I'm going to look both these patterns up in the suffix array, and I'm going to find the contiguous sections of the suffix array where they occur. And so now I'm just going to look at these lists of locations where they occur. And so what we would really like is we've got something that's really big paired with something that's really small, these sets. What I would really like is I'd like an algorithm that is not linear in the sum of these sizes, but depends mainly on the size of the small set. Right? So maybe I can reduce the dependence on the size of the large set. And the algorithm that does this, there's a very clever algorithm. It's not that old. It's published by A.C. Gates a couple years ago. It's called double binary search, and it's ridiculously simple. So first, introduce some terminology. He calls the small set the query set and the large set the data set. And you can maybe see where this is going. Now imagine that these lists of locations were sorted. They aren't sorted. Okay? We saw earlier that the list of locations is not sorted by number. It's sorted lexicographically. So these aren't sorted. But in this algorithm, let's assume for the moment that they're sorted. And I'll show you how we deal with that problem later. Double binary search. So the basic idea is if these lists of patterns were sorted, what we could do is for every element of the small set, we could look it up in the large set using binary search. And then we would get something that's basically a Q log D algorithm. And so we can actually improve on this using the following method. What we're going to do is rather than look for the patterns in the query set in order, what we're going to do is we're going to select the median element, and now we're going to do binary search in the data set for the median element. Now regardless of whether we find it, what we've just done is we've split this problem into 2 recursive subcases. And so now these can be processed using exactly the same method. But so here what we might do is we might take the median element of this set and search for it in the data set. And now here's what happens. Every once in a while, one of these recursive cases will result in a case where one of the paired patterns is empty. And so what this means is that I don't have, essentially this is a recursive base case. I don't have to deal with this and I don't have to deal with that. So what this means is I can actually stop the recursion somewhat earlier than you might expect. And so empirically this tends to yield really good results because that query set is sparse, and so you'll get this strange recursive case quite often. And the complexity, again, is going to be Q log D. But whereas in the previous case where I searched for all patterns from the query set in the data set, that Q log D is a tight bound in that case. But in this double binary search algorithm, it's actually a very loose upper bound. And so in practice, this is actually even much faster than Q log D. And there's a little note here. We only want to use this if Q log D is less than the linear sum of the size of the set. So if the sets are actually close in size, then Q log D would actually be superlinear. And that would be bad. So what we do is we check for this. Now again, since this is a loose upper bound, we don't necessarily want to check for this directly. So we add a little fudge factor, which is a lambda, which we can set empirically. So now remember, we have to have sorted sets for this to work. So let's back up for a second. We looked up our patterns in the suffix array again. So now we need to get them in sorted order. So here's what we're going to do. We're going to sort using the stratified tree that we saw earlier. And again, that's log t. So now, so that's great. We get sorted sets, except now we have another problem, which is that we just increased our complexity by log t. Oh, that's not quite right, but it's log t times q plus d, which is superlinear. I'm sorry?
I'm confused. What is t in this case?
T is the size of the text.
The entire text?
Yeah, so that stratified tree actually depends on the number of possible values that your set can take on.
So stratified tree is a separate data set that you've built from the training corpus, so it's persistent. It's not.
No, it's just a data structure that I use for sorting in this case.
But it gets created per look.
Yes.
And why would it depend on the size of the corpus?
It's a artifact of the data structure itself. I could explain it, but I'd rather explain it offline. It's a neat data structure. It's kind of obscure. But anyway, the point here is by sorting with this thing, and my complexity notation is completely off there. It actually should be, that second term should be Q plus D times log t. But the point is that this is superlinear in the size of those sets. So now we've just completely destroyed the benefit of doing a sublinear search. But this has a really easy solution, which is that once we sorted those things once, any subpattern that we look up and we compute its collocation with other patterns, we're actually to compute collocation with lots and lots and lots of patterns, hundreds of them. So we do this sort one time, and then we cache it in the prefix tree. And then for all subsequent pattern lookups involving this pattern, we can just use the sorted set. And so now we solved this problem for this first case. And so here again was our baseline in our prefix tree. And now the empirical time goes down quite a lot to about 400 seconds. And so that's nice. And so now we have to deal with the second problem. Now I want to compute the collocation of patterns that are both frequent. So and again, so now we have a slightly different problem. And just as we did before, we want to use some clever algorithm to compute the collocation of a frequent set and another frequent set. And the problem here is that there is no clever algorithm to solve this problem. It just doesn't exist. If you know one, please let me know. And so the solution is we're just going to cheat. We're going to pre-compute the collocation of anything in a small list of about 1,000 really, really frequent patterns. Right? So I'll show you on our example data. So there's our text, and here are the most frequent patterns. The two most frequent patterns, they both occur 4 times. And so what I'm going to do, I'm going to make a list of pre-computed patterns involving both of these frequent patterns. And here's what they are. Essentially, everything in that list crossed with itself. Right? So I'm going to pre-compute the locations of all of these frequent patterns. And for this example, we'll use a max phrase length of 10. It's very simple. The first thing we need to do is need to get the list of the most frequent patterns. We can do that in a single pass over something called an LCP array, which we can do offline. And the next thing that we're going to do, in order to pre-compute the pattern locations, we just have to walk over the text one time. So we start with the first element, and since it occurs on the list, we're going to add it onto a queue. And then we're going to start walking along our text, and when we find another element from the pattern, we add it to a list, and we keep walking. So now, when we get to this point, the first item on this queue compared with the current location, is actually outside of that maximum phrase length. So since we know that that first item on the queue is never going to be collocated with anything further on down the corpus, we're now just going to compute its location with all the other items on the list. So we take it and we compare it with this one, and so we add that to the appropriate location. And we do it with that one, and we add it to the appropriate location. And so we're basically just going to walk down the corpus and pre-compute this list of collocations. It's done in a single pass. It's actually quite efficient.
Single pass. Overall or per pair of patterns?
No, single pass over once over the whole corpus for all of the list of patterns. I actually have 1,000 most frequent patterns of up to length 5. That is 1,000 of all lengths, but there are patterns of up to length 5 in there. Yes?
Sorry, I missed what's the max phrase length?
The max phrase length basically says that I can't extract, say, a phrase that spans 20 words in the training corpus. The rules that I extract can have a maximum length on the number of words on the training corpus that it can extract.
X it means 2 its within 6 words?
Yes.
Do you worry about sentence boundaries?
I'm sorry? Yes, I do. Yes, I worry about them. I won't talk. It's actually quite easy when you're walking over the corpus. Whenever you see the sentence boundary, you just stop and process everything you've seen so far and then re-empty and start over. This is quite easy. So here's our timing results again. Now, if I just had the prefix tree and the precomputation, the precomputation saves a lot over the original prefix tree implementation. Not as much as the double binary search. Now, when I combine them, now this is much closer to what we want. So this is the best that we can do with these 3 algorithms. And although this is still slowing down our decoder quite a bit, it's not slowing it down by an order of magnitude. Recall our decoding takes about 10 seconds. And so from 2,000 seconds to 40 seconds, that's a pretty good start for this. This is actually something that is sort of feasible now.
It was 10 seconds.
Yeah, the decoding. So it takes 10 seconds to decode once I've looked up all the rules.
This is precise.
So obviously this approach, it requires memory, because we got to keep all these things in memory. It turns out that essentially in order to keep all of the data that I need for this, excepting the precomputation, which is going to depend on the number of patterns that I precompute, the data that I need, excepting precomputation, turns out to be about 1.3 megabytes for 30 million words, which is pretty reasonable. Now the precomputation depends on, obviously all of these things depend on the corpus size, but the precomputation is also going to depend on the number of frequent patterns in my list. And so I was actually able to simulate the memory versus speed trade-off. And so that looks like this. Actually, we get most of the benefits, just by pre-computing, the top 200 or 300 patterns. But you can keep going, and maybe you'll get a little bit more of a benefit. And again, hopefully, I'm currently actually re-implementing this in C, and hopefully it scales down, I'm hoping, by about a factor of 10. There's one other detail I want to talk about, which is the results I showed you earlier involved a prefix tree that I erased after each sentence. But remember that we can actually keep that prefix tree between sentences if we want to do batch processing. So if we do batch processing and we just keep the prefix tree in memory, we can actually do slightly better. We can bring that empirical computation down even more. So if you're decoding the NIST sets or whatever, you might actually be able to go a little bit faster. So this is sort of basically the outline of the algorithmic parts. And so this is going to allow us to look up things online. We can look up things of arbitrary length, hopefully. Yes?
I'm just wondering, if you just simply cache the most frequent patterns, most frequent, what sort of gain do you get?
I don't know. So in a way, actually doing this and doing this, there's an overlap there. And so actually one of my lab mates suggested to me the other day, well, don't do the pre-computation at all. Just compute things as you find them and keep them in a cache. And so the trick with doing that, in order to make it work in an online setting, you have to have some kind of caching strategy that says, I keep part of the tree, after the sentence is done, because if I keep the whole thing, eventually I'm going to run out of memory. So the trick there would essentially be, you could imagine any number of caching schemes, like maybe how much time it took me to look it up. If it was a long time, maybe I want to leave it in there, or if it was on my hit list, maybe I want to leave it on there. Or maybe if I've just seen it a lot recently, maybe I want to leave it on. So there are a number of different strategies, and so I essentially just sort of took these as being opposite ends of the spectrum, and you can imagine it would be somewhere in between there. Except, of course, if you don't do precomputation, then it may go up. So I'm not really sure, but there's a big space in there. So now we can do online lookup. That's great. The nice thing about these types of algorithms is that doing online lookup, you essentially get the longer patterns for free. Right? Because in all those 31 seconds there, most of the time is spent computing patterns that are like this, where I have one word followed by a gap followed by another word. Right? So probably 15 seconds are spent doing those, and then another 14 seconds are spent with 3 words, and then it goes down very quickly. It decays very quickly. So looking at patterns that have more and more words, actually, it's essentially free. So that's a nice thing. The next thing we're going to look at is sort of relaxing some of the gap sizes. But the point is, we can actually now compute very, very large grammars that you wouldn't really dream of doing in the offline setting. But I'm actually interested in doing some other things with this. So here's some problems, sort of the basic outline of problems that you have in machine translation. This is from like a survey by a smart fellow that was released recently. So we know that we have to do modeling in machine translation. Almost all the work in machine translation, focuses very heavily on the modeling. Well, I have a phrase-based model, or I have a word-based model, or I have a hierarchical model, a finite state model with discontiguous phrases, syntax-based model, syntax-aware, all kinds of modeling, which basically deals with the shape of the way I translate and the type of rules that I use. Parameter estimation, there's still a lot of maximum likelihood. There's the minimum error rate training is really common. Now people are experimenting with perceptron algorithms and decision trees and maximum margin methods. And so a lot of this is going to come from the machine learning community. We have to solve the decoding problem. There's a lot of algorithmic work on that. Evaluation, which causes religious wars. And then, so one thing that actually has sort of not really been addressed, really extensively in the MT literature is feature engineering. Basically, if you look at the features that are used in the standard systems, they basically inherit directly from the IBM models. I got the phrasal probability of E given F, the reverse probability, a lexical probability, which basically goes back to the IBM models, distortion probabilities, and maybe some count features. And so last year I actually did some feature selection experiments on these 8. These are the standard 8 features that are used, and most of them don't really help very much. We get the first 3 that are sort of diverse, and then after that it sort of goes down. The improvements fall off very quickly. But one thing that we know from other problems in natural language processing, part-of-speech tagging, semantic inference, parsing, is that using a diverse set of features can help a lot. So here's a question. So online lookup can actually help us solve this problem. So now imagine I'm translating an input sentence, and I look up a particular phrase that I want to translate in that input sentence. When I look it up using this online lookup, I find that source phrase and its translation in context. I don't just find the phrase and its translation. I find the sentence that it occurs in. And optionally, you could imagine maybe I part-of-speech tagged or parsed my corpus. So maybe I can load those things up, and I can actually get a very, very rich context of that phrase as it occurs in the wild when it's translated. And so the question now is, essentially whether we can compute interesting features when we have that context available to us. You can't imagine that I could compute, for instance, a sentence similarity feature between my input sentence and the training sentences in the corpus using a table-based method. But using online lookup, I could actually, for instance, look at the sentence I'm translating for the particular phrase and see if I could find sentences that are very similar to that, and then weight those translations more heavily. So this is the type of feature that we're looking at. Also annotation-based features. And so this is actually work in progress. So I don't have full results on all of this, and I don't have all the details available. And I've been working on this in a contiguous system. And so far, we're getting some improvements over the table-based baseline. And hopefully those are going to go up pretty soon. So this is one thing that we're very interested in doing with online lookup. And so another thing I can do is more of an algorithmic approach. So let's look at these approximate pattern matching algorithms, which is really what this talk is about. They mainly come out of computational biology. One thing that approximate pattern matching is used for really extensively is search in protein databases. So, I have some source protein sequence, a DNA sequence, and I want to find similar DNA sequences in a database. Essentially, you compute some kind of score function between your input pattern and the patterns in the database, and you go look them up and rank them. And this is used for sequencing and phylogeny and motif identification. So one thing I think would be interesting would actually to treat machine translation as lookup in a protein database. So rather than simply restrict ourselves to phrases with two gaps and some small number of words, we could have an arbitrary number of gaps, arbitrary number of words. And essentially, what we want to do is, with an extension of this algorithm, essentially a very straightforward extension, just relaxing all the restrictions, we could try to find in our training corpus of millions of sentences the sentence that is as close as possible to our current input sentence, and just extract that kind of thing wholesale along with its translation. And this starts to look something like maybe example-based translation. And so, maybe we have a few holes we've got to fill in. We can fill them in with standard phrases. And this is something I hope to work on after I defend my dissertation. So the possible decoder architecture looks like something like this. I get an input sentence in, and I get a match which maybe a large number of words, and all I have to do is maybe fill in these little gaps here. So this is basically it. I'm showing you a pattern matching algorithm, which I think is going to solve a lot of interesting problems in machine translation. And that's actually it. So I'd be happy to take questions.
Do you have any experiments that might indicate how likely one is to actually find long example-based matches?
I'd like to do this. I haven't had time to do this yet. So this is fairly speculative.
So the illusion you had with 0.7 improvement in the blue score just a couple of slides back was based on what?
That's based on using online lookup in a contiguous phrase-based system, where I relax some of the length restrictions, and I also add in some of these features. Actually, not any of those features, but some really, really dumb features, actually, that computed from the context. Yeah.
In this experiment, what the phrase bands of the baseline system?
4, 5.
So the algorithmic methods you sort of outlined seem really quite interesting. And it's interesting also that you're sort of drawing on the computational biology stuff. The other thing that this reminded me of was some of the kernel work. I don't know how familiar you are exactly.
Yeah. Super familiar.
I mean, the basic idea behind kernel approaches in machine learning is to say, rather than extracting features, keep the training data around, and whenever you sort of want to evaluate what would be the features, in fact, actually just go back to the training data and take the match.
This is very much along the line, because I originally sort of wanted to compute these types of features, and I realized there was just no way to do that I compute a bunch of tables offline, but essentially what we're doing is we're using the training data as an indirect representation of all of the features that we want to compute.
Yeah, and so, I mean, again, also, I'm not a great expert in string kernels, but I mean, and in fact, I don't even know if those guys, if the work at string kernels is sublinear in the length of the training data, which I guess is what you managed to achieve, right? Lead is something.
Yeah, so the part of the problem, this is sort of a special pattern matching problem because in a standard case of, say, pattern matching with gaps, I just get one pattern and I have to look it up. And so if it takes 5 seconds to look up one pattern, that's okay. But now I have to look up thousands of patterns and I have to do it very quickly. So I don't know. It's not entirely clear to me because I'm not a computational biologist, and I also haven't done any work in string kernels. I don't necessarily know what the other applications are. I would be interested in taking a look at them, and hopefully it would do something useful. But I actually don't know the answer to that yet.
All your examples were with a single gap, but Hierarchical uses 2 gaps.
Yes.
I assume that you just simplified it for expository purposes.
Yeah. So
you've done it all for 2 gaps.
So let's. Yeah, I actually did this. I had the full model in all of the experiments. So here's what happens. In this case, if I've got 2 gaps, then what I do is I perform one computation at a time. So essentially, first I look up A, then I look up B, then I look up C. Well, actually what I do, first I look up A, then I look up B, then I compute A x B. Then I look up C if necessary, and then I compute this. Right? So I'm always looking at a pair of locations when I'm doing this.
When you generalize to more gaps, the initial one already have gaps.
Yeah. So sort of recursively through the prefix array data structure, essentially what you do, you pre-compute, you don't pre-compute, but you compute all the gaps at the beginning. And then the subsequent computations become very fast. So in an m-length source sentence, there's I guess m squared gaps, actually less if you're imposing restrictions on the phrase length. So essentially the very first thing you do is you compute those really expensive gaps, and then you're just adding words on either side. And so the runtime decays very rapidly.
The end result of the whole computation that you talked about here is a index into is a list of corpus positions that those patterns start from, right? But that list can get quite long.
Yes.
So then do you have to do something special to deal with the length of that list, or do you does that even factor in?
Well, again, so the only list that I have to keep permanently, that I'm keeping permanently, is this list. And so I've already looked these up, and so this is a fixed amount of memory that I'm using.
Those are the subpacks.
These are the ones that I pre-compute. So now, if I'm doing the online matching for other patterns that aren't in this list, I look them up and I find the list of locations. Then when I'm finished processing that sentence, I can throw them away.
But when you find the list of those locations, what do you then need to do with that list? Do you need to look at the list at all, or do you just need to know the length of the list to get the frequency?
You actually need to, once you have the list of locations, you actually go find the patterns. Then you extract the phrases they align to, and then you compute the phrase probabilities. So I didn't talk about that. Essentially, that problem was basically solved in the Callis and Birch paper. And they have to do some additional tricks. Like, so if you find something that occurs 1,000 times, or 1,000,000 times, say, you don't actually extract all of them. You extract a sample of them. But actually, most patterns occur less than 1,000,000 times, obviously.
And your cached patterns presumably are the ones that occur very frequently.
Yeah.
So then do you pre-compute the phrases for these, or do you
No,
just
I don't pre-compute the phrases. Although, I mean, it would be... So it would be straightforward to pre-compute the phrases, but there's a little bit of a trick there because... So some of the features like the phrase probability, that you can just compute once and then you're done. But if you're looking at a more contextual probability, then you may have to go back and look at that list every time. So there's some amount of work you can do up front. It just depends.